Hey folks, welcome to my channel number 10. There we have the problem on our screen. The graph of f is shown below. State with reasons that x values the numbers at which f is not differentiable, right? So we have a graph in front of us, and f of x is represented by the pink line. What you see, the green lines are the x and y axis. The pink lines are a representation of the curve. Now we will have to examine the curve and figure out which points are not differentiable, right? So the moment I look at this curve, I notice that there are 4 points of concern, right? Point one is the point here, right? I'm just gonna mark it, which is -1. I don't think it's represented in the graph, so let's call that out. And then we have 4 as another point, and then we have 8, right? And then we have 11, right? So there are basically 4 points. I don't think we will have to really be worried about the other points in this curve. And let's examine it one by one. So let's start with -1, right? So as the curve moves through -1, you see that there is a very sharp turn, right? We also know that dy dx, which is nothing but your f dashed, right, which is the derivative of a function, is also an indication of the slope of the tangent to the curve at a particular point, right? So f dashed of x naught is nothing but slope of the tangent to the curve at that particular point x naught. So what happens at this point x naught equals -1 is before the point -1, just before the point -1, you see that the curve would take a slope in one direction, and just after the point -1, right, the curve takes a slope in the other direction, right? So so it's very evident from the graph that it changes direction, and it changes direction as the curve passes through the sharp uh, point x equals -1. So there is a turn, and therefore dy dx changes direction at the point -1, right? And in the world of mathematics, and specifically in the world of differential calculus, we call this as a cusp, right? And I'm going to write this. A cusp is CUSP. So in this case, we really do not know what the equation is, but it looks like, as I draw a tangent through the point -1, it is seems like a vertical tangent, right? So vertical tangent means the slope is infinity, right? And because the curve changes direction as it moves through the point -1, what happens is in these cases your d by dx for the left hand derivative, if it is say positive, then your right hand derivative will be negative. And similarly, if your left hand derivative is negative, then your right hand derivative is positive. And why is that? Because the curve changes direction as it moves through the sharp uh, cusp -1, right? And we call this a vertical cusp when you know that the slope of the tangent at the point or at the cusp, in this particular case -1, is infinity, right? Which means that we have a vertical tangent through the point -1, right? So, keeping all this discussion aside, whenever you see a sharp edge or a sharp corner and the graph changes direction, right, as we move through the point, then you can possibly conclude that such functions are not differentiable at this point. In this case, we call this as a cusp, and therefore the function is not differentiable at these points, right? So this is the case with -1. And I want to cover the point 8 before we come to 4, because this is again a very similar case, right? Again, you see a very sharp edge at the point 8. And while we do not know what the function definition is, we know that d by dx, as we move through 8, right, will change direction. So the left hand derivative will be in one direction and the right hand derivative will be in the other direction, right? So what happens in this case, it is again a cusp, right? And you can definitely conclude that the function is not differentiable at the point x equals 8. So these 2 points are indeed cusps, right? And in the same category, in the world of differential calculus, you will come across corners, right? And I just wanted to take a minute to tell you what is the difference between a corner and a cusp, right? So, in a corner is very similar to a cusp, but what happens is we use the terminology corner for specific functions when we are very sure that a left hand or right hand derivative exists, but they change direction, right? So what happens in this case? What is this? We know this function very well. This is mod of x, right? So mod of x, what happens is for x lesser than 0, you see that this is the curve, right? You can see that, I'm just going to call it region 1. And for x greater than or equal to 0, you have this region 2, right? So what happens is this function is a continuous function, but what happens is we have a corner at the point x equals 0, and we generally use the term corner for these functions because in these cases your left hand and the right hand derivatives will definitely change direction and the function is not differentiable. But when you actually work out f dash of x naught plus an f dash of x naught minus, you will see that they will have finite numbers, right? They will not be infinite, right? So in this case, for example, when you do mod of x, you will notice that your f dash of x naught plus will be plus 1, and your f dashed of uh, x naught minus will be a minus 1. So in these cases, you will notice that my left hand and right hand derivatives do exist. They are finite numbers, and these are called as corners. In this particular case, we don't have the function definition in front of us, but still it very much looks like our left hand and right hand derivatives will tend towards pl- um, infinity, and one will tend towards infinite in one direction and the other slope, which is your other derivative, will tend in the other direction. So in effect, your left hand and right hand derivatives are going to tend towards plus or minus infinity respectively, or minus or plus infinity respectively, right? So that is what happens in the case of a cusp. And in the case of a corner, what happens is that your left hand and right hand derivatives are finite numbers, right? Like we saw here in this particular equation in the case of mod x, right? Where your left hand and right hand derivatives are finite numbers, right? So with this, we know that -1 and 8, 2 points, are not differentiable, right? So let's move to the next point now. Now, the next point we'll pick up is the point 4. So, what happens at 4? We see that, at the point 4, we have the curve undergoing a jump, right? And we know what to call this type of functions. These functions are exhibiting a jump discontinuity at the point 4, right? So what happens for x lesser than or equal to 4? This function takes this portion of the curve, and for x greater than 4, this function starts to take uh, this portion of this curve, which I just highlighted, right? Which is this one, right? So it's very evident that my f dashed, it's very evident that the function is discontinuous at the point 4. It exhibits jump discontinuity. And in this case, the function is continuous from the left. And why is that? I want to draw your attention to the shaded circle out here, right? Which is this one, which means that this is the value that the function takes when x equals 4. And it is a part of the left hand portion of the curve, which, let me call it region 1. And it's a part of region 1. And you will notice that your function f of 4 will be equal to your left hand limit, right? So what happens is this function is continuous from the left, but is discontinuous from the right, okay? Because the function uh, on the right of 4, which belongs to region 2 as highlighted in this graph, does not include the value 4, right? So what you will notice is your left hand limits and right hand limits are not equal, right? So the function is discontinuous, right? And if the function is discontinuous, you can always conclude that the function is not differentiable, right? So discontinuity implies non-differentiability, whereas a function which is continuous does not necessarily imply uh, differentiability, right? And we have an example for that, the one which we saw earlier, mod of x. So you will see that mod of x is a continuous function, but it's not a differentiable function at the point x equals 0, right? So that is an example of when a function is continuous but is not differentiable at a particular point x equals x naught. So again, remember this, folks: a function which is discontinuous is always not differentiable, whereas a function which is continuous does not necessarily imply differentiability, right? So we that's how. So we can straight away conclude that at the point 4, the point is discontinuous and therefore it is not differentiable, right? So we've examined 3 points: minus 1, 4, and 8, right? All the 3 points are not differentiable, but for different reasons, right? So minus 1 and 8 belong to the same uh, category of reasons, and 4 belongs to a different category, right? So that's the highlight of this particular problem. It helps you understand how to identify graphically a function is differentiable or not. And then we come to 11, and we'll have to make a small assumption out here. You see that at 11, right, before and after 11, the function more or less looks like a straight line, right? So what happens is this function is a clear case of a tangent being perpendicular to the x-axis. We call it vertical tangent in the world of differentiable calculus, and it means that the slope at the point x equals 11 is perpendicular to the x-axis and is infinite, right? Why is it infinite? Because the slope is nothing but tan theta, where theta is the angle made by the slope with respect to the x-axis, right? And in this case, it being a straight line, the angle is 90 degrees. And what is tan of 90? Tan of 90 is infinite, right? And therefore, the tangent is vertical, right? Again, it is a case of non-differentiability, right? So we have seen all the 4 points, and we can definitely conclude that all the 4 points are not differentiable for this particular graph. Three important things to summarize, right? One is whenever you see a sharp edge and the curve changes direction, it means that your left hand and right hand derivatives are not equal, right? And when it is a cusp or a corner, right, you will notice that the function is not differentiable at those sharp edges, right? So that is point one. Second is whenever a function is not continuous at a point x equals x naught, then we can definitely conclude that the function is not differentiable. However, a continuous function does not necessarily imply that the function is differentiable at that particular point, right? And we saw a good example of that, which is mod x, right? And then the third important thing is straight line. We have a case of a tangent which is perpendicular to the x-axis. We can comfortably conclude that the function is not differentiable. So with this, we've come to the end of the video. I hope you found this content useful. Please do subscribe to my channel and support. Thank you.